this is a slide from Graham Hancock, which Neil just mentioned. And, certainly in terms of this discipline and, telling this new story, like he mentioned, Graham Hancock's new book, Magicians of the Gods, a sequel to Chariots of the Gods from 20-something years ago, is pretty much the definitive work on this, along with his collaborators like Robert Schoch. And I can't tell you enough how awesome Graham and his work is. Nassim Haramein certainly drew upon Graham's work in being able to make these connections between the ancient culture geometries and the modern physics. Because what Nassim found is that the geometry of space-time is very much in perfect resonance with this structure. This is a resonating cavity within the geometry of the structure of space itself. And to just briefly try to go into it a little bit deeper, what we're talking about when I say the geometry of the structure of the vacuum itself, I'm talking about vibrations that are so small that it's inconceivable. I mean, you think about your own body, okay? We can relate to ourselves. We're made of 100 trillion cells approximately on average, depending on whether or not you count all the bacteria in your gut and things like this and the organisms living on us and stuff. But if we have 100 trillion cells and there's about 100 trillion atoms in each one of those cells, it means we're made of quintillions of atoms, quintillions of structures that are all made of smaller structures, that are quantized, called protons, and protons really are the fundamental particle of the universe. When we measure the mass of the universe, protons, because everything else is negligible in terms of their mass. And so inside of a proton are even smaller quantas of energy. This is something that was coined by Max Planck, and that's why they're called the Planck's distance. And incredibly small distance. It's such a short distance that if you took the scale of the smallest thing that we know of, the smallest thing that you can measure, which is the Planck's distance, it's basically the width of the smallest photon of light. You can't see anything smaller than a photon of light because light can't bounce off of it and hit your eye, right? So this is not the smallest thing that exists. It's the smallest thing that we as human beings at this time in our bodies, using our technology, we have no way of accessing any information smaller than the Planck's length. It's the smallest possible measurable distance in math and science currently right now. And then you look at the other side of the spectrum, right? The observable universe. We can't observe anything outside of our universe right now. We think the edge of the universe is approximately 13.82 billion years ago. And of course, that's changed just in my lifetime. When I was a kid, it was 13.7. It's already now 13.82. Wait till the James Webb telescope goes up. That's going to be 100 times more powerful than the Hubble. They'll probably do another deep field shot and be like, oh, there's galaxies farther than away. The age of the universe just got older. If you're 65 or older right now, you were told that the universe is 3 billion years old when you were in school. So, man, the rate at which we have to change the textbooks in all the disciplines is actually speeding up faster and faster at this point. So now we've got the observable universe and the Planck's distance. Such an incredibly large change in scale. It's unfathomable. But guess what halfway in scale is? No, it's not a galaxy. No, it's not a star. No, it's not a planet. No, it's not even a human. It's about the size of the smallest thing that the human eye can see. Like a tardigrade. Have you ever heard of these guys? The little water bears, they're called, right? That can actually survive in space. They've figured out these guys can dehydrate themselves and rehydrate. The size of a tardigrade is about halfway in scale of the entire universe as far as we can tell. Halfway between the Planck's distance and the observable universe. Well, the Planck's, the little vibrations that are called Planck's, there's 10 to the 60 of them inside of a proton. 10 to the 60 is a 1 with 59 zeros after it. If you have like a bank account with 6 zeros on it, you're stoked, right? And if you put one more zero on there, you've just gotten yourself 10 times more money. So imagine a bank account that's got 60 zeros on it. You put one more on there, you're 10 times, right? So you're estimating like the number of particles in the universe, 10 to the 78. If you say, no, it's 10 to the 79, that's 10 universes, right? It's a big change. 10 to the 60 Planck spherical units, the little vibrations in a proton. Let's make each one of those the size of a grain of sand. If you took 10 to the 60 grains of sand and you put them together, the diameter of your proton would be from here to Alpha Centauri, something like 4 trillion kilometers away. 4 light years away. So, man, the Planck's distance is humming inside of everything, and if you get enough Plancks together and they coordinate their motion, you get a proton, and you put enough protons together, you get an atom, and if you put enough atoms together as quantas, you get molecules, which is a larger quanta, and you put more molecules together, you get more complex things like proteins and DNA, and eventually you get to us and the material world that we see. And so we're finding that the geometry, that the way that the Planck spherical units are vibrating is around a tetrahedral array. If you put a sphere around each one of these tetrahedrons, you get a three-dimensional structure that is spherical waveforms overlapping, and they're centered by these vectors of tetrahedrons. Basically, what I'm describing is a three-dimensional flower of life symbol. The flower of life you guys have all seen everywhere, and it's all over the place in ancient cultures, including in Egypt. And the flower of life is the geometry of the sphere packing of the Planck's pixels that are inside of protons. And we see it exhibiting in fractal scales as we get bigger and bigger, this relationship between the sphere and the tetrahedron.